Module 6, Chapter 3.5, Higher Degree Polynomial Functions and Graphs. Remember, a linear function is a function of the form f of x equals ax plus b. It is what we call a degree 1 function, and the graph is going to be a straight line with a slope of a and a y-intercept of b. A quadratic function is a function of the form f of x equals ax squared plus bx plus c, and it is called a second degree function, and the graph of a quadratic function is a parabola. These are both examples of polynomial functions. A polynomial function of degree n in the variable x is a function defined by p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on, all the way down to a sub 1 x plus a sub 0, where each a sub I is a real number, and a sub n is not equal to 0, and n is a whole number. And I know that sounds like a lot to remember, but what it is x to the n is your highest power, and then your powers decrease by 1 all the way down until you have an x term and a constant term. The a sub n is simply the coefficient of the x to the n power. The a sub 1 is simply the coefficient of x to the first power. A sub n can't be equal to 0 because then we wouldn't have an x to the n term. A sub n is called the leading coefficient, and a sub n x to the n power is called the leading term or the dominating term. A sub 0 is called the constant term. P of 0 equals a sub 0 is the y-intercept of the graph of y equals to that p of x function. Unless otherwise specified, a polynomial function has a domain from negative infinity to positive infinity. Also, the graph of a polynomial function is a smooth, continuous curve with no sharp corners. The cubic function is a third degree polynomial of the form p of x equals ax to the third plus bx to the second plus cx plus d, where a is not equal to 0. In general, the graph of a cubic function will resemble one of the following shapes. This is the basic shape of f of x equals x to the third. This is f of x equals negative x to the third. And these two graphs show up when you have x to the third and maybe some squared terms or some x terms or some constant terms. Now the quartic function is a fourth degree polynomial of the form p of x equals ax to the fourth plus bx to the third plus cx to the second plus dx plus e, as long as a is not equal to 0. Notice we always set these up. If it's a fourth degree, that means the highest power is 4. And then we go ahead and include all the lower powers. In general, the graph of a quartic function will resemble one of the following shapes. The dashed portions indicate irregular but smooth behavior. This is typically your f of x is equal to x to the fourth graph, and this is your f of x equals negative x to the fourth graph. Sound familiar? Sort of like your x squareds? Well, these, we can have graphs that do all kinds of things in here on these dotted lines. May just come up or down once, but these will depend on the third, second, and first powers of your x terms. Now, extrema, we've talked about extrema. These are turning points, or where the graph of a function changes from increasing to decreasing, or vice versa. The local maximum point is the highest point or peak in an interval. Function values at these points are called local maxima. Now remember, the values are simply the y values. The local minimum point is the lowest point or the valley in an interval. The function values at these points are called local minima. Extrema, which is plural of extremum, includes all of the local max and local min points. Now, the local maximum point is the highest point in some interval on the graph. The absolute maximum point is the highest point on the whole graph. The local minimum point is the lowest point in some interval on the graph. The absolute minimum point is the lowest point on the whole graph. Just remember, local means for just some particular area. Absolute means for the entire graph. Okay, as a note, a function may have more than one absolute max or min point, but it can only have one absolute max or min value. Okay, for example, if you have a function whose graph looks like this, and we'll call P1 is x1, y1, P2 is x2, y2, and point 3 is x3, y3. Point 2 is the absolute max because it's the highest point for the whole graph. It's a local max because it's the highest point just for this region of the graph. Okay, P1 is a local max because it's the highest for this area, but it's not the highest for the overall graph. Now, what about point 3? Point 3 is a local min because it's the lowest for this area. Is it an absolute min? No, because you have points going down on both sides, so there are lowest points on the graph. Now, over here, if we had this shape of a graph, point 1 is a local max because it's the highest on this interval, but it's not the absolute because you have other y values going up. Same thing for point 2. It's a local min because it's the lowest for that area, but it's not the absolute min because we do have points down below it. Now, consider the following graphs. Let's call this graph 1, and let's call this graph 2. Name and classify the local extrema of F1 and F2. Of F1, or actually we'll call that f of x, we have the ordered pair AB is a local min. We have the ordered pair EH, which is a local min, and it's also the absolute min because it is the lowest. We have point CD, which is a local max. It's not the highest point, so it's not the absolute max. Now, describe the absolute extrema for F. Well, we just did that, didn't we? EH was the absolute min. There were no other absolutes. Now, name and classify the local and absolute extrema of G. Well, MN is the local max because it's highest for that area, but it's not the highest point. JK is the local min. It's the lowest, but it's not the lowest for the entire graph. Now, a linear function has degree 1 and no local extrema. Why not? Well, the graph is a straight line, and there are no turning points. A quadratic function has degree 2 with one extreme point. It's either going to look like this, or it's going to look like this. Each of those have one turning point. A cubic function has degree 3 with at most 2 local extrema. A quartic function has degree 4 with at most 3 local extrema. The number of turning points of the graph of a polynomial function of degree n is greater than or equal to 1 is at most n minus 1. You know what? You are just ruining my whole video. Go away. Shut the door and go away. Pain in the rear end. As a general rule, the number of turning points of the graph of a polynomial function of degree n is greater than or equal to 1 is at most n minus 1. Now, identify the type of polynomial function and the minimum number of turning points. So if our function is f of x equals x to the third plus 5x minus 9, then we say that the degree is 3. So there are at most 2 turning points. And we call a degree 3 function a cubic function. G of x equals 6 minus x squared. The highest power is 2, so we're going to call that a degree 2 equation, which it could have at most 1 turning point. And we call this a quadratic equation. H of x equals 4x plus 7. That is a degree 1 equation, or degree 1 function, which can have at most 0 turning points. And that is what we call a linear function. Now, m of x equals x to the fourth plus 5x to the third minus 2x squared plus 4x minus 1. That is a degree 4 equation, which we call that a quartic, which will have at most 3 turning points. And then, which is a degree 5 equation, which we could just say is a polynomial function with at most 4 turning points. Now, in behavior, remember ax to the n is the leading term. And all of these polynomial functions will break down into 2 categories. They will either have a parabola-shaped graph, or they will have this S-shaped graph. And what you'll find out is, if a is greater than 0, if the number in front of the x to the highest power term is positive and n is odd, your graph will always start down in the left-hand corner, go up, and finish up in the top right-hand corner. If the coefficient is negative, then it flips. It reflects across the x-axis, and it starts up high, and then it comes and it finishes down low. Whereas if your power is even, and the first term is, and the coefficient is positive, then you get our x to the squared general graph. Or if the leading coefficient is negative, like negative x to the second, then both ends go down. We're going to match each function with its graph. Now the first graph is x to the fourth power. So that's an even power, which means they're both up or both down. Because it's a positive x to the fourth, both endpoints go up. So this is our f of x graph. Now g of x is negative x to the sixth. Well, that's x to the sixth is an even power, so they both go up or they both go down. And the negative means they're both going to go down. So this one is our g function. Now h, that is our 3x to the third. X to the third is an odd power, which means it's going to start down low, and as it goes from left to right, it's going to go up. So this is our h to the h of x graph. And then k of x is negative 7x to the seventh. That's also an odd graph, so one goes up, one goes down. But because the coefficient is negative, that means it starts high and ends low. So this would be our k of x graph. Now let's see if we can predict the end behavior on the following graphs. It's an x to the third. That's an odd power. One goes up, one goes down. Because it's a positive coefficient, we know it's going to go something like this. Now, 6 minus x squared. Because it's x to the second, that means they're both up or both down. Because it's a negative x to the second, then we know both endpoints are going to go down. Now keep in mind, I'm not saying this is where this graph is, and there's a lot of stuff that could happen in here. Same thing for this one. It's not the actual graph, but we do know that both ends will go down. 4x plus 7, that's x to the 1 graph, which means one starts down and goes up. And in this case, it just so happens that this one is linear, so we know it's going to take off through that. X to the fourth plus 5x to the third minus 2x squared plus 4x minus 1. That's an x to the fourth. That's an even. It's a positive x to the fourth, which means both are going to go up. We don't know what's going to happen in here, but we do know that both endpoints will go up. And then our x to the fifth plus 12. X to the fifth is an odd. It's a positive coefficient, so we know it's going to start down here. We don't know what's going to happen, and then it's going to take off up to the far right. Now let's switch gears. X-intercepts. A polynomial function of degree n will have at most n x-intercepts, or at most n real zeros, or you can think of these as solutions. Now consider the graphs of linear, quadratic, and cubic functions. Linear functions are straight lines, or they will have at most one x-intercept. It could either have one x-intercept, or it could have 0 x-intercepts. Think of your quadratics. It could have 2 x-intercepts. It could have 1 x-intercept. Or it could have 0 x-intercepts. Think of cubic functions. They could have 1 x-intercept, or it could have 1, 2, 3 x-intercepts, or it could have 2 x-intercepts? Sure, it could come up, touch it here, come down, cross it here. But if it's an x to the third, then it can only have at most 2 turning points, which means it can have at most 3 x-intercepts. Okay, now, using your graphing calculator, see if you can find the x-intercepts of the polynomial function x to the third plus 5x to the second plus 5x minus 2. So if we pull up our calculator and we graph y equals x to the third power plus 5x to the second power plus 5x minus 2, and we'll go to zoom 6. Always start us out with the nice window. There's our graph. We have 1, 2, 3 x-intercepts. Now remember, this is like finding the solution where it's equal to 0. So what we're going to do is we're going to go down to y2 and we're going to make y2 equal to 0. And we're going to find where those intersect. So second trace, number 5, enter, enter, enter. So we get our first solution as 0.3. So we're going to come over here, and the first x-intercept is 0.30. The second one, second trace, number 5, enter, enter. This time we're going to move it over right here, and we get -2. So x is equal to -2. Third one, second trace, number 5, enter, enter. Move your cursor on the one that we're looking for, and we get -3.30. So, and you be careful on my math lab because sometimes it'll say enter the x-intercept as 0.30, -2, and -3.30, and then other times they will just say list the x-intercepts or list the x values only. Now, given p of x equals x to the 5th plus 2x to the 4th minus x to the 3rd plus x to the 2nd minus x minus 4, determine its domain. Well, if you'll notice that there's no square roots and no x in the denominator, then we know that the domain is -infinity to infinity. Now, what's its range? Well, we may have to look at the graph. So if we want to put this in our calculator, we get x to the 5th plus 2x to the 4th, and so on, the whole function. We press graph. So if we're looking for the range on the calculator, if you'll notice this graph goes all the way down, this graph goes all the way up, so the range would also be from -infinity to infinity. Okay, next it says use its graph to find approximations of local extreme points. We have a local max and a local min. So we can do second calculate number 4, which is the max. We're going to go make sure we're on the left side. Whoops, lost our cursor. Left side of the lowest, highest point. Right side of the highest point. And we would get a maximum of -2.019, 10.010. That was our local max. Local min, same thing. Second calculate number 3. We're to the left of the lowest point. Cross over. We're to the right. Press enter, which would give us 0.408, -4.243, and that would be our local min. Then it says use its graph to find the approximate and or exact x-intercepts. Well, we know there's 3. It looks like one is at 1, one is at -1, and one is between -2 and -3. We can find them. Just make sure we've got the equation in y1, y2 is 0. Second, calculate where they intersect. Enter, enter, enter for the first curve, which would give us an intersection at x equals 1.141. I'm glad we didn't have to just guess and go with it. We're going to do second calculate the intersect of the second point. Enter, enter. On the guess is when we're going to move our cursor over. And we get an x-intercept of -1. One more time. Second calculate number 5. Enter, enter. When it says guess, we move our cursor. And that says that our last one would be negative 2.518. So that would be our 3 x-intercepts. Okay, now it says give the intervals over which the function is increasing, decreasing, or constant. Well, it's increasing all the way up until we hit this local max, which remember this was our local max right here. So we say that it's increasing on the interval from negative infinity to negative 2.019. And then it starts decreasing from the local max all the way down to the local min, which means it decreases from negative 2.019 to x is 0.408. And then it starts increasing again at 0.408 all the way up until infinity. Now, comprehensive graphs. Remember, the comprehensive graph means that you want to be able to see all of your intercepts, all of your extrema, and the end behavior. A comprehensive graph of a polynomial function will exhibit all x-intercepts, if there are any, the y-intercept, all extreme points, if there are any, and enough of the graph to exhibit the end behavior. For example, use your graphing calculator to sketch the comprehensive graph of p of x equals 0.045 x to the fourth minus 2x squared plus 2. So we're going to go to y equals, and we are going to enter 0.045 x to the power of 4 minus 2x squared plus 2. Let's go back to Zoom 6. Now, is that a comprehensive graph? Well, it almost is. We know the general shape of it, but we don't know how far down the graph goes at those 2 points. So what we can do is we can go to Window, and we can just change your y minimum. Let's try negative 20. Will that be enough? Works for that side, works for that side. So that could be a comprehensive graph. Now, the window negative 1.25 up to 1.25 by negative 400 to 50 is used in the following graph. Is this a comprehensive graph? Well, what you've got to look at is this is an x to the sixth. So yes, both ends are going up, but there could be at most 5 turning points, and we're only seeing 1. So if we plug this into our calculator, x to the sixth minus 36x to the fourth plus 288x to the second minus 256, and the window they're using is negative 1.25 for the x up to 1.25. And then the y values go from negative 400 to 25. And if we graph that, we would get what's shown over in the picture. Okay. Zoom 6, let's do Zoom 6. That might give us a little bit better. Well, that actually looks worse, but that just says there is a lot going on. Let's go to Zoom 0, which is Zoom Fit. Well, that didn't help us a lot. Let's go back to Zoom 6, which is our standard window. That one showed more of our graphs. And now let's go to Zoom Out, which is Zoom 3. Press Enter. That still didn't work. Let's go to... Okay, looking at this one, all of our x values are good. So let's change our y values. So let's go to Window. Let's leave our x's from negative 10 to 10, and let's change our y values from negative 100 to positive 100. Let's see if that's going to help us any. Well, that's getting there. Let's go to negative 1,000 up to 500. Okay, this is what we're talking about when we say a comprehensive graph. It shows your highest values, your lowest values, and all of your intercepts. But hopefully they're all not going to be this hard to find. You're ready to do your homework on this section in my math lab.